those legacy infrastructures. The technology of wholesale CBDCs, what we
Some
see from
Hyperledger
the
thing that's going on
projects,
right now.
the pilot projects at
Mhm.
this point, is that it's mostly predominantly DLT. So it is used
Watch.
as tokenized money, as tokenized
Restream.
central bank digital currency. So it is accessible to, I mean, the representation of the money is as tokens. And the requirements to introduce wholesale CBDC is that it has to be highly interoperable with other payment systems. The transaction speed has to be increased compared to the one that is incumbent in a country, which can be measured by transaction per seconds, and to lower the transaction fees, which is the biggest problem
Okay.
of all.
I think this looks great. I want to watch this some other time. So let me add this to the thing.
The first approach could be to the enhanced compatibility model of CBDCs. What does that mean? Multiple CBDCs and transfers are handled by private settlement companies. So every central bank develops its own wholesale central bank digital currency system. And then they let the companies which have a presence in each country to handle transactions, handle wholesale CBDC transactions through their banks. So those banks who have an international presence have a huge advantage because wherever they are, they can access central bank digital currencies and they can settle them with them. Interlinked CBDC systems. Interlinked CBDC systems can happen via a technical interface or a centralized clearing system or decentralized clearing process. What does
Mm,
that mean? It is similar to the previous one. So every central bank develops its whole CBDC system to replace its a real-time gross settlement system, the incumbent one, and then via technical interface or clearing processes, those systems are interconnected. So it's not the banks and the bank subsidiaries who are connected to each other. It's the whole banking system of each central bank's jurisdiction that is interconnected. And the third one, and the most integrated one, is the single system for multiple CBDCs. So it's a single multi-currency system, a single rule book, and a set of participation requirements, which means that there is only one system where the central bank digital currencies are minted, are created, and settled. There are no distinct systems in place. All right. Why are wholesale CBDC systems necessary? Because there are a lot of frictions in the current correspondent banking arrangements, the correspondent banking system. As you might know, nowadays, if you initiate a transaction, it has to go through a lot of banks to reach an international destination. And the transaction itself has very limited
you
transparency.
know, so I think this is pretty much good for now. I just saw this thing and I thought, why not click on it? It said live. So, um, is this? I don't want to watch that. Okay, so this is interesting. So why was this interesting? So central bank digital currency. So the thing we're about to do next is basically um, we're gonna go to our terminal here, and we're gonna create this unbroken chain of Alice's. And in doing that, we're going to establish, first off, we're going to establish an identity, right? And so there's some comments basically, what we'll do in the future is we'll link Web 2 identity with Web 3 identity. But for now, what we're going to do is we're going to focus on TBDEX as our bid mechanism to get jobs done. We're going to focus on DIDs as manifests um, in order to uh, like DID methods, I think is probably more of the right term, as manifests, which we're using TBDEX to bid on. Um, and this central bank digital currency thing is interesting because we're the way that we're going to do bids. So so system local resource management. So what was that issue all about? Well, back long time ago now, um, when this project started. This was all about cloning Git repos, and so if you're cloning a lot of Git repos, you're gonna run out of disk space, right? So the goal was how could we facilitate somehow, this theoretical system local resource management. It's gonna help us. It's gonna help us. It's gonna help us. You know, Basically manage our underlying resource as is applicable to the locality of what we're trying to reserve, right? Which is the system local locality, right? Disk or seek groups or whatever, right? Basically we're on this system. Okay, that's our locality. And so now we've established that we're basically going to be able to, use input operations and traverse our graph to determine locality and help us, have other operations with input, output, do time of, we'll have to do some. Ooh, how can we do that? Oh, well, we have locking, so I think we can hopefully. Yeah, we should with the hierarchical locking stuff. That should help us with time of check, time of use on this. We're gonna have to double check that, um, but it should help us with that. Yeah. So yeah, that locking stuff will actually do this for us. Yes, I will. Perfect. Okay, well, where are we going with this? So basically, yeah, let's go look at TBDEX and see how we can. So what we're going to do is we're going to issue a request. So we're going to have multiple types of system contexts, right? And we'll probably have DIDs we'll probably implement DID methods for each of them. So there's the DID peer. So basically what we found out about DIDs is that, you know, there's the identifier and then there's the method on the identifier. So this maps perfectly to our sort of, always one level deep concept, right? So we can make a DID method for every single operation. And the ID will basically encode, the ID will be the unique ID for the arguments that we gave for that method. And this way we can use, these peer DI, or the DIDs in general, and their associated docs as the manifest, because the DID, including the method, encodes the schema, and then and possibly also within the, the schema could potentially be, yeah, you could encode the. We have to find a way to get the schema out of there. So maybe it's a mapping. I don't really love that. It doesn't really encode the schema for you. So we'll probably have to say a DID method that includes a schema within the data of the DID or the DID doc, basically. So things like that service, um, uh, if it includes, if it has like a little, they'll require some section that's kind of like service that we're going to need for all these manifest style DID docs, so that we can have the spec, the the spec in there, when the spec should probably be referenced as another DID, and then, or the schema, I mean. So we should have a DID for the schema. Yeah, okay, let's do it. So we should have a DID for schemas, and I think I might have seen a schema DID in there. Um, where is, okay. Okay. So, okay, so treat DID methods as uh, uh, manifest right? Because a manifest is a contract, right? So we can basically accept these DIDs. We can use DBDEX to bid on the DIDs, right? And the DIDs will be the jobs that we're bidding on doing, right? And the jobs that we're bidding on doing are the operations, and the operations may be a whole data flow, right? And so forth. Okay, so treat DIDs as manifest. As this is manifest. So we need to make sure there's a DID schema. DID. Okay, and then, whatever the method name is, or let's say maybe operation name. Okay, so, and how would we appropriately scope that? So basically we would say, DFFML, so DFFML, or maybe we should say, because this is no longer really DFFML, this is the implementation. So open architecture, open architecture, yeah, and then maybe the data flow, ID, and then the operation name. Okay, open architecture, the data flow ID, and the operation name. Because, yeah, so this is a method which exists on that data flow. Or, well, it's going to be, it doesn't really even need to be open architecture method. Or we'll just call it manifest. Schema and manifest. Okay, great. Schema and manifest. Okay. Okay, so we can use the manifest for encoding operations. Use TBDEX to create bids. So create manifest DID method. Define. So we need to define the manifest DID method. We need to use TBDEX. All right, so what are we doing? So define manifest DID method. And why is this remember, we're treating everything as a supply chain, right? So if I'm going to basically, because we're doing this data flow based approach, right? So if I blow up one piece, I need to rebuild those pieces to get back to where I'm supposed to be in the chain, right? So define the manifest DID method. So it will have the, okay. Okay, define manifest DID method. You know, yeah, okay. And then the system context itself, system encode. Okay, so make fields for system context attributes. So we can leverage update mechanisms or DID update resolution. We can leverage DID update resolution mechanisms if we define as a DID method. Okay, so DID, I saw somewhere that basically there's the way that is it the pure DIDs or is it the DIDs? conflict resolution, followed by pure DIDs. Deltas do not make conflicts. Okay, so these are early micro ledger for backing storage. Backing storage is dependent on ledger technology. Requirements are somewhat relaxed. Yep. All we need is close to triple signed receipts, not a ledger or blockchain maintained by pure consensus. Yeah. What we need is a closer to the approach of triple signed receipts or CRI, not a ledger. Yeah, see, this is different. This is why this is the critical thing that makes this different than the rest of blockchain. Um, okay. Um, see that, and this is just okay. So maybe we need to build on pure DIDs. Can we build on pure DIDs? Is there sort of like some kind of concept of subclassing so that we can treat? Okay. Okay. Encode a public key directly as a and generate a very simple DID document. Okay, DID key. Either can derive a public SSH key. Can we use our SSH keys for this? Well, it doesn't really matter. We can just sign something with an SSH key and then call it good. Let's see. What kind of algorithms does this support? That would be pretty cool if we could use SSH keys. That'd be pretty cool. Using SSH keys simplifies everything. How do we create? Okay, so what we're going to do now, okay. Oh my God, if we can use SSH keys, we can bind all this. We can bind all this to TPMs. Like we can, if we can use SSH keys, we are in business. The business of free stuff. If we can use SSH keys. Let's see. Okay, so this would be if we can use SSH keys. If we can use SSH keys, that'd be great. That would just simplify things a lot. Public format. It doesn't really matter. Okay, how could we do that? So we could basically say, yeah, it doesn't matter. We could use something like it. That doesn't matter. Here's SSH key. Is there some kind of, Okay, so these pure DIDs, CRUD operations. Although creating a pure DID and the Genesis version of its DID doc can be done at any time, it does not require registering a pure DID with another party. Relationships requires a specific protocol. The only protocol that must be supported by implementation that targets layer 2B or layer 2B support. Okay, so create register general recipe. Given the stored variant of a pure DID doc to a remote party in a way that guarantees Give the stored variant of the DID doc to a remote party in a way that guarantees no other party knows the DID values of the content of the DID docs, the confidentiality guarantee of traditional security analysis. Given the stored variant of a DID stored variant. Creates a stored variant. Okay, method one. Okay, generation method. A unique numeric bias underlying a pure DID must be generated in one of the following ways. So I think we need, yeah. So inception key without doc. If numalgo equals 0, for example, DID key blank is equivalent to DID. Okay, so a single key, I mean, no. Public key value is a pair for a numeric basis of the DID. The Genesis version of the DID doc is considered to be empty, granting all privileges to this key. Okay, so basically method 0, so basically if you just create a regular DID key is a DID peer. Okay. Okay, the DID doc offers it. No endpoint. Okay, this is important. Okay. Okay. Okay, so DID key is a method 0 DID peer. And then let's go ahead and link so that we maintain our chain of information. Okay. Okay. So inception key without doc. Okay, so we need to create, okay. So if we do not have an identity, we are going to create an identity by creating a new DID key. This is going to be basically our root asymmetric key, right? All of our trust relationships are going to be based off of this, or going to be tied back to this key for this entity. And you can blow this up at any time is the thing. So we'll save it by default, right? So we can basically have. So we talked about in the thread. There's some stuff about basically like we can just reuse the concept of overlays, and we can basically have this sort of like location, like you can have this thing that runs on startup, right? And you could configure it to use whatever overlays you might usually choose for your user, right? So maybe you load them from your home dir or something, right? It doesn't matter. You'll have it, or you'll have this itself will be a data flow, right? And you can change it with an overlay. Yeah, so basically default overlay maybe. Will have default overlay setting, top level context overlay setting, overlay switch to command line, add and high level run. Okay, so okay, and then use this to pass data flow, which might load from dot local, right? So you might load some more stuff from your home dir or somewhere else. Always require argument. People can make aliases if they want to aliases or use environment variables to set if they, okay. Always require argument, never load from disk a default, right? So basically, always load via env vars or CLI or Python API. Never assume disk. Okay, basically never assume you have a disk on this for this project. Let's just not. So always assume data flow, right? And that way it'll be configurable. Okay, I'll be back.